Hello, and welcome back to Calero Academy. Today, we will be going back, as promised, to find the surface area of a cone. Now, in this video, we will be looking at 3 different approaches, and the first 2 approaches will be the most interesting, whereas the last one will be the most simple. So, now, let's begin. In the first approach, we are going to do something similar to how we found the volume in our other video. So, you remember that if you rotated this line around the x-axis, then you will get a cone. And we found the volume of that cone by just summing up with the integral the area of each of those circles. So, now we're going to do something similar, but instead we are going to be adding up the circumferences of each of these circles, thereby getting the surface area, the lateral area, that is. Where the difference between the lateral area and the surface area is that if we draw a cone, a little bit ugly, anyway, the lateral area being this area, where the lateral area does not take into account the circle at the bottom of our cone. So to get the real surface area, we have to add pi r squared, the area of the circle at the bottom of our cone. So, our lateral area will be equal to the integral from a to b of 2 pi y ds. And let me explain that. So, y is going to be the formula for this line, which we will find very easily in a couple of seconds, and ds is our arc length variable, which we might remember is equal to 1 plus 1, the root of 1 plus r squared on h squared in this case. Because, in fact, I'll explain why that is true in a second. So, y is equal to, if we let this be the radius of our cone and this be the height of our cone from here to here, then y is just equal to the line with slope r on h. So it's r on h times x. That's the equation of our line. Now, the differential ds is equal to, and here it's wrong, it's supposed to be ds dx. So ds is equal to the root of 1 plus the square of the derivative of y, the derivative of f of x dx. And this comes from the definition of arc length. And therefore, when we take the derivative of y, we get r on h, and when we square that, we get this. So we can now substitute into our formula for the lateral area, and we will get that LA is equal to the integral from 0 to h times 2 pi times r on h times x times ds, which is equal to this, so times the root of 1 plus r squared on h squared dx. And so now all we have to do is just integrate this, and we get that it is equal to 2 pi times r on h times x, times the root of 1 plus r squared on h squared times the integral from 0 to h of x dx, which is quite simple. So when we now take the integral of this, we will get that our lateral area is equal to 2 pi times r on h times the root of 1 plus r squared on h squared minus h squared on 2. Times h squared on 2. Sorry about that. So, this the root of 1 plus r squared on h squared is equal to the root of h squared plus r squared on h squared. So, the root of h squared plus r squared shows up quite a lot in our area for our cone, so we give it a special name, the root of h squared plus r squared. We give it the letter L. And so we can simplify this as being equal to L on the root of h squared, which is equal to L on h. And therefore we can rewrite our lateral area as being equal to 2 pi times r on h times L on h times h squared on 2, which is equal to pi r L. And that is the correct lateral area of a cone. And to get our surface area, we just add pi r squared. So it's pi r squared plus pi r L. Okay, so that ends our approach 1. Now for approach 2. In approach 2, we are going to look at something that is somewhat similar. It's a distant relative of this. So, turns out that the surface area of a surface is equal to the integral from a to b of the integral from c to d of the root of the derivative of a multivariable function. So actually, let's pause here. And so the double integral approach relies on us expressing our function in terms of two variables. And since we're going to need more space here, so let's expand our root sign. So it's the derivative of a multivariable function with respect to x squared plus the derivative of a multivariable function of the derivative of f of x of y with respect to y squared plus 1 times dy dx. And we will get this inner expression from looking at some definitions of the integral for our double integrals. And with that in mind, now that we have this little expression, we can now try to substitute in some stuff for this. So, we found in the other video that f of x and y is equal to h on r times the root of x squared plus y squared. And we got that by looking at what happens when we place our cone on a three-dimensional coordinate system. Okay, so now what we have to do, now that we have our function for our cone, we will just take the derivative with respect to x and with respect to y, and then just plug that in. And since it's a little bit tedious just plugging all that in, I'll just do it all in one line, and we will get that our lateral area is equal to the integral from 0 to, and so what we're going to do here is that we are going to also, after we simplify this, it turns out that it's a monster to take the derivative of, and it's much easier. It turns out that, okay, it's not a monstrous thing to do, so I'm just going to plug in some random constants. We'll get that it's equal to the integral from a to b of the integral from c to d of a very simple expression, L and R, with respect to y and x. So the reason that this is hard to integrate is not because it's hard to integrate the actual formula, the actual function in here. That's very, very easy to integrate because it's just a constant. We know what L and R is, so that's very constant. So What's hard is to define A, B, and C, D. Those are very tricky constants to define by looking at this. So it's much easier instead to put it back into this entire expression, to put it into polar coordinates. And we'll remember that when we switch to polar coordinates, dy dx is equal to cap r times d cap r d theta. And so our lateral area will be equal to the integral from 0 to 2 pi of the integral from 0 to r of L on r times cap r with respect to cap r and theta. So, now that we have this, we can now progress to do some easy integration, and so we'll take out, so we'll have the integral from 0 to 2 pi of L and r outside of the integral of cap r from 0 to r, which is just going to be equal to, times r squared on 2. And we got that by just taking the integral of cap r and taking the limits of integration from 0 to r. So it's this, taking the integral of L and r times r squared on 2 with respect to theta. And now, after a little bit of simplification, after we take this out, we will have L times r on 2 outside of the integral of from 0 to 2 pi of nothing, just 1 d theta, and that's going to be equal to theta. So it's equal to it's equal to theta from 0 to 2 pi, and that's equal to 2 pi rl on 2, which is equal to pi rl. And again, we can find our surface area by adding pi r squared to pi rl, our lateral area. And now, with our two most interesting approaches done, we can now look at a very nice and sneaky approach to finding the area. It's very simple. It involves no calculus at all. We find it by remembering something. If we look at a sector of a circle, and so we can now move up our paper a bit. If we look at a sector of a circle, imagine if we cut off a piece of a circle. What's the area of that sector of the circle? So after a little brief examination, we'll see that the area is equal to pi r squared theta on 2 pi, which you can see very easily by realizing that this is just saying multiply it by the fraction, how many angles you have of this circle, that fraction over 2 pi, and multiply that to the area. So it's just very simple. That's the area of that circle, of that sector of the circle, and that's equal to r squared on 2 times theta. Now, think of it. When you look at a cone, all it really is a sector of a circle wrapped up on itself. And so let's look at this. Let's imagine that this is our cone when it's unfurled. So what we're going to be finding is the area, the lateral area, of course, because the area of the bottom of our cone is no longer there. So, what is r in this unfurled cylinder? So, let's go back to looking at our real cylinder. L is equal to the distance along the surface from the top of the cone to the bottom of the cone, so that's L. It's not the line going straight down to the bottom of the circle. It's just it's the slant height. It's the line that goes from the top all the way down the surface. So it's the same L. So, and of course L is equal to, again, the root of r squared plus h squared, because by Pythagoras. Because of Pythagoras. So, L, when we unfurl our little cylinder, we'll get that the radius of this sector of the circle is L. And you can experiment with this by cutting off a piece of paper and experimenting with making your own cones by yourself. And so that's our radius. Now, is that it? No, because what is this part of the circumference? I mean, what is the circumference of this sector? And the circumference of this sector is equal to 2 pi times the radius of our cone, which again you can get by imagining what happens when we unfurl this cone over here. So we have from our base here, r. So this will be equal to 2 pi r. And our area says the area of this sector says it's equal to r squared on 2 times theta, where theta is in radians, of course. And what is the definition of a radian again? It's equal to the radians of an angle will be equal to the oops, sorry about that. Whack the camera. So anyway, so the definition of the radians of this angle, the angle of this angle in radians is equal to the circumference subtended divided by the radius. So the definition of this angle in radians is theta is equal to 2 pi r on L. So our lateral area is equal to r squared on 2 times, okay, actually, sorry, so wait. So our lateral area will be equal to 1/2 of the radius, which in this case is L, so it's L squared on 2. We already did that. 1/2 of L squared times theta, which we said is equal to 2 pi r on L. And so our lateral area, sorry for not writing the equal sign, so our lateral area is equal to pi r L, and that is again the correct answer. And to get our surface area, again, all we have to do is add r pi r squared. And so this concludes this Calero Academy video. We hope you enjoyed it. If you have any questions, or if you have another approach, for example, if you saw an error, please put it down in the comment section and we'll look at it and possibly make a video about it. So thank you again, and goodbye.